2. And in 11.2, we're going to talk about continuity. Instinctively, you know, intuitively, what happens when a function is not continuous, because you've talked about continuity in previous algebra classes. Okay? A function is not continuous, and this is the concept you should have of it. A function is not continuous if you put your pencil anywhere on that function and you start tracing it along with your pencil, and at some point you have to pick up your pencil and move it to another place to continue tracing. You know intuitively that that function is what we say discontinuous, where you had to pick up your pencil. Okay, now that is a good way to judge when a function is discontinuous. But calculus gives us a mathematical justification for saying that a function is discontinuous at specific points. And it's a 3-step process. The first thing you look, if you're trying to decide if a number is continuous at, or a function is continuous at any number C, that number can be anything, positive, negative, rational, irrational, just some number C. 3 things are required for that function to be continuous at that point C. The first thing that's required is that f of C exists. You can plug C into the function and it gives you a number. It gives you an answer. Okay? F of C has to exist. If you try to plug in f of C and it causes you to divide by 0, it fails the first test because f of C doesn't exist. If you plug in whatever number C is into the function and it causes you to take the square root of a negative number, well, then f of C doesn't exist. It's not real. And therefore, step 1 will fail. If step 1 fails, you don't go on to step 2 and step 3. The first time you fail, you say, no, you're done. You're not continuous. Doesn't matter if it's discontinuous in one single point, then the function's not continuous. Okay? Period. Not continuous, period. Now you can say, as long as I stay between this number and this number, this piece of the function might be continuous. Because the discontinuity is numbers less than one end or more than the other end. So you can talk about continuity on what's called a closed interval from, let's say, -5 to +2. It may be completely continuous on the interval from -5 to +2, but it may be discontinuous at 4. But see, 4 is not on the interval from -5 to +2. Okay, so you can talk about it being continuous in pieces, but maybe not be continuous everywhere. The second step is that the limit as x approaches that number C also has to exist. And we know from the last chapter the only way that that limit as x approaches that number C can exist is if you approach C from the left and you approach C from the right, they come together at a single value. They're on the collision course. If the left-hand limit and the right-hand limit are equal, then the function has passed the second test because the limit exists. But if f of C is defined, but then the limit doesn't exist at C, then you say, no, it's not continuous then. Okay? It's not continuous. Once you get through the first 2 steps, the last step that proves it is truly continuous is that step 1 is satisfied and step 2 is satisfied, but the answer to step 1 must be the same as the answer to step 2. The limit from the left must equal the limit from the right, and that also equals the value of the function at C. So we're going to walk through some examples here and talk about how this works. This one says, determine if the function graphed at the right is continuous at x equals C. The first question you ask yourself for step 1 is, what is the value of f of 3? Because we're trying to approach 3. Okay? It isn't actually, because if you notice, 3 is right here. If you read up to the function, you see an open circle. Okay? So f of 3 is undefined. Which is synonymous with it does not exist. The number 3 exists, but the function doesn't have a value at x equals 3. Therefore, it has failed step 1. And because it failed step 1, the function is not continuous at x equals 3. Okay? It is not continuous there. You can also say it is discontinuous at x equals 3. Because discontinuous and not continuous mean the same thing. Okay? So we would say that this function has a discontinuity at the value x equals 3. Anybody have any questions? Okay, fail the first step. We don't even have to go to step 2. Yes.
So if there was a dot that was filled in above that, would it be continuous or just?
It might still be continuous. We have to check.
Oh.
Okay? So yes, if f of 3 was like 4, then that step would check off. F of 3 equals 4. Then we would move to the next one. And see what happens in the next step. But as soon as it fails, you don't have to finish the process. Just stop where you are and you're done. Okay? And I will run across one like we're talking. In fact, it's right here. Here's a function, h of x. We're looking at h of x where x is equal to 0. What is the value of h of 0? Is it defined? Yes, h of 0 is defined. H of 0 is defined as -1. H of 0 is -1 because that's where the point's filled in. It isn't defined as +1. Notice there's a hole where +1 is. So it says no, at x equals 0, h takes on the value -1. It doesn't choose the value 1. Okay? So then we go to step 2. Does the limit of h of x exist as x approaches 0? Well, let's approach it from the left and then from the right and see what happens. I'm going to approach it from the left. So there's the limit from the left. The limit as x approaches 0 from the left, which is what that little negative sign is saying, is equal to -1. Okay? So then I have to approach from the right and make sure this all works. So I'm going to come at 0 from the right-hand side. And when I take the limit as x approaches 0 from the positive side of things, because this is positive, and the other end is the negatives. But as I approach 0 from the positive side, it's approaching the value 1. Okay? Is the left-hand limit equal to the right-hand limit?
No.
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 Therefore, the answer to that question is no. And that's because the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right. So we passed step 1 just fine, but we failed at step 2. And for that reason, the function graphed at the right, h of x, is not continuous at x equals 0. Yes, ma'am.
I'm sorry, but I guess I'm just having like a hard time grasping, like, even though, like, the limit exists, but there's a hole at 1. Like, you know what I mean? So I just thought 1 wasn't on the graph. So I guess.
The .01 isn't on the graph. You're correct about that.
Okay.
And that actually is what causes the discontinuity, is because that if we did actually have both the .01 and 0, -1, both of those were on the graph, it wouldn't be a function. Okay?
Okay.
So h of x is still a function because it doesn't have two different values when x is equal to 0, but it's not continuous at x equals 0 because it breaks apart.
Yeah.
And what calculus tells you about it breaking apart is that's when your left-hand limit and your right-hand limit don't come together. Okay?
Okay.
So that's what makes it fail at step 2.
So the limit is not there because they're not equal and they don't come together, and it's not continuous at x equals 0 because.
The limit doesn't exist.
Okay.
That's the reason this time. The limit doesn't exist.
Okay.
First, the function has to have an actual defined value at that number. Well, it did. 0, -1. So step 1 checked us off, but step 2 we failed because the limit didn't exist. The function has to exist and the limit has to exist, both.
Okay.
Okay? And since we failed at step 2, then we don't go any further. We don't worry about a third step. Okay, so here's another one. Determine if the function graphed at the right is continuous at x equals 4. Okay, first question. What is the value of g of 4? It's 1. The name of that point is 4, 1. Okay? So that means we've passed step 1. We're okay on step 1. So then we move to step 2. Does the limit as x approaches 4 of g of x exist? Well, let's see. I'm going to approach from the negative, which means I'm going to follow g of x until I get really, really close to 4, and I see that what it's actually approaching is -2. Okay? So the left-hand limit exists. So if I come at it from the positive side, then the limit as x approaches 4 from the positive side of g of x is also -2 because I'm approaching the same point. The point 4, -2. So does the limit exist? Yes. Those are equal to each other. So it exists. Okay? And in fact, the limit as x approaches 4 of g of x is equal to -2. We good so far? Sure. Okay? Now we've got to continue looking at it because we have one more step. So remember, we've determined so far that g of 4 exists. There it is. We have also determined that the left-hand limit and the right-hand limit of g of 4 exists. So g of 4 exists, and g of 4 is equal to 1. The limit exists. And in fact, that limit is equal to -2. So then we have one last question. And this is where we're going to fail. Does the limit equal the value of the function?
No.
No.
Okay, so that's what we're
1 does not equal -2. Therefore, we have failed at step 3. G of x is discontinuous at x equals 4. Okay? You have to pass all 3 steps. If you don't pass the first one, you already know you're not going to pass all 3, so you don't worry about steps 2 and 3 if you fail step 1. You have to pass all 3 steps. Okay? So here we've got another one. The function is f of x. F of x is probably what we call an exponential decay function, because from the point -2, its values, its function outputs approach 0, but it never crosses 0. It just gets smaller and smaller and does so very quickly. Is f of -2 defined? That's correct. Why? What is it on this graph that tells us that f of -2 is not defined?
It's an asymptote.
That's right. That dotted line is an asymptote.
I said there's nothing.
That means -2 is not in the domain of f of x. So for that reason, f of -2 is undefined, and this function is not continuous. We say that f of x is discontinuous at x equals -2. Okay? Any questions so far? The calculus should be just backing up what you know realistically. If I had asked you that question and not taught you any calculus, if I had asked you, is that graph continuous at x equals -2, you would have said, No, because it doesn't go anywhere after that. It just approaches -2. It never crosses it. It doesn't ever connect up with the other side. Okay? But calculus gives us a reason why. This one's a little trickier because I didn't show you a graph. Graphs are easier to tell where the discontinuities are because we kind of visually know. But unless we graph the square root of 5x plus 3, we do not visually know where that function might be discontinuous. So what we do is, well, we could graph the function, and it will back up what we're going to figure out, but we're going to figure this out first algebraically. Thou shalt not do what?
Divide by 0.
Okay, am I going to divide by 0?
No.
Then what else shall I not do on pain of death? What can you not do that involves radicals? Can't take square roots, fourth roots, sixth roots, no even roots of negative numbers. Therefore, what would cause me to violate that rule would be if 5x plus 3 were to be equal to or less than, actually it could be equal to because equal to would work, so we'll just say less than, if it is less than 0, because we can take the square root of 0 without a problem. Okay? That means that 5x is less than 3 and x would be less than 3 over 5. So this function, based upon what we just found, is discontinuous at x equals 3/5. And since we're going to pursue it on the calculator, I'll give you the decimal value of 3/5, that's 0.6.
Shouldn't it be -3/5? Is there a positive 3/5?
Ah, yes, it should be. Thank you. Thank you, thank you, thank you. Okay. Now we're going to verify that on the graphing calculator. Once you get your calculator, see if I can get this where we can actually see what's on here. So I'm going to type in the square root of 5x plus 3, close the parentheses, and I'm just going to hit zoom 6. Can you see that graph? So my graph looks like this. Okay? To sketch off my calculator, my graph looks like this. That value right there is negative 0.6 or 3/5. Yes.
How do you graph that again?
You go to y equals and enter second x squared, which gives you your square root.
Okay.
And then you put in 5x plus 3. And then you close your parentheses.
And then zoom 6.
And I did zoom 6 because that's the what we call the standard window, which goes from -10 to 10.
It keeps on giving me that.
Okay. Okay, anytime it gives you that particular error, see what it says?
Invalid dimension.
It won't let you do anything but quit. But if you go to your Y equals menu, here's where your problem is. Put your cursor on top of lot 1 and press enter and turn it off.
Okay.
Okay, and it should work just fine now.
There it is. Thank you.
Okay? Now, if you can't graph it and get to see what I'm seeing, then you need to let me know so I can figure out what's going wrong. Okay? Now, in order to test out the idea that the problem truly is that it is discontinuous at -3/5 or -0.6, what I'm going to do is I'm going to hit second trace. I'm going to choose value. And I'm going to enter the fraction answer that I got by solving 5x plus 3 is less than 0. And that answer was -5 divided by 3.
I'm sorry,
I mean,
Ms. Flint. Can you go back through that, please? You're trying to do what? Find out that
I'm trying to find out that where, and I know this is hard to see,
they're, -3/5.
I'm trying to find out what happens on that graph at x equals -3/5. Because I can see that if I come at it from the right, it seems to stop right there.
Yeah.
So when I do that, I hit second trace and choose 1 for value and type in my fraction, -3/5. And I hit enter.
You gotta put it in that parentheses.
You don't necessarily have to on this one. If it was a more of an arithmetic problem, you would. It won't hurt to put in parentheses. And what I see is that it tells me at -0.6 or -3/5, the value of y is 0. Okay? So what it's telling me is that's where it actually touches the x-axis. But if I were to go more negative than -3/5, let's say go to -2, it says, no. -2 is not in the domain of this function. That function doesn't exist over at -2. Okay? So where the function actually is discontinuous is for all x values that are equal to or actually all x values that are less than, not equal to, but less than -3/5.
Makes sense.
Okay? Now, I want this to make sense to you. This is the one section out of chapter 11 that should make sense to you. Because continuity is something that you've talked about before. Your mind kind of knows what it is. You've just not ever had to talk about using calculus to explain it. Okay? What are we worried about here? We're worried about an asymptote. Asymptotes happen when you divide by 0. We cannot allow x to take on a value in this function that would cause us to divide by 0. So in order to find out where that might happen, we actually try to plug in a number for x that will let us divide by 0 by setting 2x minus 7 equals 0. So x equals 7/2 or 3.5. Okay? So does f of 3.5 exist?
No.
No. So for that reason, f of x is discontinuous at 3.5 because f of 3.5 is undefined. It fails step 1. Okay? We don't have to go on and test limits and all that other stuff. It fails step 1. Okay? Okay, here's another function. Are there going to be values of a that we can't plug in for x and then raise e to the 2x minus 3 power? Okay, I don't see any square roots. Do you? No. I don't see any division problems. I don't see any fractions where x is in the denominator. Do you see that? So what do you think is probably true? Since those are the only two things we worry about,
Then it's continuous.
it's probably continuous everywhere. It's probably continuous everywhere. So tentatively, we're going to say we think it's continuous, not discontinuous, everywhere, or in other words, for all real numbers. Okay? Now, just because we haven't hit on anything that bothers us, we still would want to back this up with a calculator and actually try to graph it. So I'm going to show you how to type it in because I know you can't see my calculator screen all that well. So you go to Y1, and the keys that you're going to hit are going to be the second and the LN key. That's how you get E. And it'll automatically give you a power sign, and it'll open a parenthesis. Okay?
You do what? Y1?
You go to Y1.
Second, that E.
You hit second and LN, which is right next to the number 4. And then you type in 2x minus 3. And close the parentheses. Hopefully with me putting it right under the light right there, you can see that. Okay? But the way that you get your E is second LN, and the LN is next to the number 4. And then you just finish out the expression for your power. Okay? And then since we're just looking around for it, we're going to hit zoom 6 just as a starting point. And hopefully you can all see that graph. What that graph does is it starts out, it appears to be at the origin, but I can't really see what it's doing after it gets to about there. I can't tell if it's maybe going through the x-axis, if it's going under it, if it's just following along it. Can't tell what it's doing. So in order to figure that out, I'm going to hit the trace button. And I'm going to see what happens if I try to trace past x equals 0 going toward the left.
go to the zero, like you're doing the x-intercept?
No, I'm just going to trace, just hitting trace. And I'm gonna trace to the left. I'm gonna keep pressing the left arrow button. And what you see happening, I'm gonna try to sketch it for you. Here's your x-axis. Here's your y-axis. As I can see pretty clearly what happens on this side. But what I can't see without tracing on the calculator is that what it's doing over here is it's just getting closer and closer and closer to the x-axis, but it's continuing on. Which means that e raised to any power, doesn't matter if x is negative or positive, e raised to any power is never going to give you a negative answer because it never goes below the x-axis. But it also doesn't have any restrictions on what x's you can put in. You can ask it for what is x equals 10 million. And it'll tell you what it is. It'll be in an ugly scientific notation number, but it'll tell you that it's just really, really extremely small. Okay? So this actually will bear out what we said to start with. It does appear that it is continuous for all real numbers. Because you can trace on that function as far left as you want to, as far right as you want to, and you're never going to hit an x that it can't plug in. Okay? So that one is continuous everywhere or continuous for all real numbers. This is one I guarantee you're going to see on the test. Not this particular problem, but one similar to this. You want to pay careful attention here. When you have piecewise defined functions, when there is a change in rule from one piece to the next, one part of the domain to the next, if you have multiple rules depending on what x is, every time that you have a new rule, you have the potential for the function to be discontinuous at that point. Okay? Now, if I were to graph this function, and I'm going to try to sketch you a graph of it to start with. I'm not going to try to do it on the calculator because this is honestly just easier. I've got to look and see where x is less than 0. And x is less than 0 going in this direction. Okay?
Glenn, what page of the notes you want? I've got a piecewise problem on here, but it's not.
Yeah. Is yours different?
Yeah, 16. Yeah.
Page 6.
We're on page 16 of the notes. It's on 16.
Let me pop it back up again. Oops, went too far. Okay, this is actually your turn too, so you're getting a freebie. Okay? The one that you have as your example is different from the one that I'm doing. Okay, so pay careful attention. You get a free homework problem here. Okay, when x is less than 0, the function is a linear function. It makes a line. All I need to do to figure out what it does over here is plug in numbers that are less than 0. In other words, plug in negative numbers. Okay? So if x is negative 1, then 5 times negative 1 is negative 5. And negative 5 minus 4 is negative 9. And if x is negative 2, Then 5 times negative 2 is negative 10 minus 4 would be negative 14. Put me all the way down here in this part, okay? Now I could use slope and keep on going down, or I could keep on plugging in more and more negative numbers, but I know it's a linear function, and I only need 2 points to graph that linear function. So I'm going to graph with just those 2 points. And my graph's not to scale, so you're going to have to kind of bear with me here. Okay? So it's a straight line. But then when x is between 0 and 3, it changes rules.
I'm so sorry. I don't want to interrupt the flow or anything, but how did you get that line? I'm so sorry.
I just plugged in negative 1. 5 times negative 1 is negative 5. Minus 4 is negative 9. So negative 1 down 9.
Okay, all right.
And then with negative 2, same thing.
I had a really rough time just now. I'm so sorry.
Okay, that's all right. Now, what I want you to understand is this would, if we were allowed to use 0, then this point should actually be negative 1, 2, 3, 4. Okay, so there, it would be there, but it's not. That big green blob I put there says, this really wants to be at negative 4, but it can't be. There's actually a hole there. Okay? But if I plug in, and here's the big question, if I plug in 0 into the rule that 0 is supposed to plug into, that's the x squared rule. What's 0 squared?
0.
0. That means I would have the point 0, 0. Okay? And if I plug in x equals 1, 1 squared would be 1. And if I plug in x equals 2, 1, 2, 3, 4. And then if I plug in x equals 3, and remember that's the end point, I'm not going beyond 3 with this rule. Then 3 squared would be 9. And 9 would be on up here. So it would be making a piece of a parabola, and it would continue on up. But it's not going to go, in this case, past 9. Because at x equals 3, it does have the value 9, and that is included, but it stops there. It stops. Okay? And then it switches gears again. And it drops down, and it says, for any number you want to plug in that's more than 3. That's everything out here. All of these numbers. Numbers like 4 and 5 and 6 and so on. Add 6 to the input. So 4 plus 6 is 10. And 5 plus 6 is 11. 6 plus 6 is 12. And that's a linear function also. So at 3, it isn't going to actually equal 9. Or is it? Let's see. 3 plus 6, yeah, it would connect up right there at 9. So here's a little better sketch of what we've got. Less than 0, 0 to 3 more than 0, or more than 3, okay?
Okay. I'm confused at how you got that last long.
Okay, let me see if I can do a better sketch for you.
Why does it connect to 9? Why does it connect to 9 thumbs to the grid?
How many colors?
We're gonna see.
You said it's easy, but I don't.
You're plugging it out. The two sides button. Plug it up. So, for this one, radiant 3, plug in number 3, 3, 4, 5, 6. It would be the same one for the other two.
Do we have one in here?
Yeah.
Is there one? Yeah. Okay, good. I was like, yeah, I can't do straight lines. I was like this. And then I try to like mold it over it so it like fills in the hole. And then it ends up looking, it's like
Okay.
this thick.
The first piece of the function, -1, and let's see, I need my definition again. -1, -9. -2. -14. And if I was going to be able to use 0, even though I'm not, I can use everything up to 0. It would be wanting to connect up to 0, 4. Okay? It wants to, but it can't. So that part of your function is the linear. This is the part where the rule is 5x minus 4. When x is less than 0, which means it's not allowed to have 0 in its domain, and there's a hole there. Then for the next, yes,
I'm sorry, so when you graph that, do you write it like that with the circle?
yes. If you're graphing it by hand, you want to put a hole there. Because it doesn't just stop at 1. It actually keeps on going up toward the axis, but it can't touch it. Okay? Now then for 0 to 3, here's 3, it turns into a parabola. And it would like to continue on with that parabola, but it has to cut off at 3, so this part doesn't exist, okay? It has to stop because this is for the part of it that is equal to or less than, so that means the origin is included. And it's equal to or less than 3, so 3 is included. So that point right there is 3, 9. That's where it ends, okay? Then it switches rules again. And this time I'm going to switch colors to make sure you understand what's happening.
Yes, please do.
Okay, so the last piece follows the rule x plus 6.
If x is greater than 3.
So if x is 4, it's 10. If x is 5, it's 11. If x is 10, 10 plus 6 is 16. So this part of it, again, is linear. And I can connect up my points. But now remember, it doesn't start at numbers 4. There are still points on that part of the rule that is for like 3.2 and 3.3 and 3.4, because this ended at 3. The next rule picks up at 3.00001, okay? this is the last part.
Wait, no, 6 is 12.
Okay?
6 plus
Now,
12.
even though that green part of the function does not include 3 in its domain, if it did, 3 plus 6 is 9. So it comes all the way up to 3, as close as it can get. And it gets really, really close to 9. So talking about this from the limit side, let's look first at the breakpoint 3. This is one of the important points. Looking at 3. That is a potential place for discontinuity. So let's apply the 3 rules, looking only at x equals 3.
Okay, so you
What is the value at x equals 3?
9.
It's 9. By the x squared rule, it's 9. What is the limit as x approaches 3 from the left? As I approach 3 from the left, what value am I honing in on?
9.
9. What would happen if I approach 3 from the right? What value am I approaching?
9.
9.
She's showing the limit, so.
And since this 9 is equal to that 9, it is continuous at x equals 3. F of 3 is defined. The limit approaching 3 from the left is equal to the limit of approaching 3 from the right, and that's equal to f of 3, which is 9. Therefore, that function has passed all 3 tests, and we say f of x is continuous at x equals 3. Even though it makes a sharp point, it comes together, it stops being a parabola and abruptly just goes off and turns into linear. It is continuous at that point. Okay?
How did you get 9? I mean, I know you squared it, but why did you square it?
Because the rule for the part of the function that goes from 0 to 3 says to take the number and square it. So if I were to have plugged in 2.9, I would have squared it because it's in that interval. Or if I had plugged in 1.5, that's in that interval, I would have squared that number. But it would have made the parabola part of it. It's because of that's this one. See, it says here, it's x squared. Yeah, you're looking at the one in the notes, and I accidentally put the wrong one up. Okay?
So we just completely ignore the bottom line.
Well, not quite. Is that function, looking at the sketch that I made, is that function continuous?
No.
Where's the break?
Between 0 and 0.
It's at 0, right? So let's examine 0. Is f of 0 defined? What is f of 0?
Oh, it's -4 there.
It's what?
Just to find out the origin.
Okay, it's defined at the origin, 0, 0, so Colin's right. Okay, f of 0 is equal to 0. Because 0 is in the middle part of that domain between 0 and 3. It's included in that second piece. Okay? So even though it doesn't use the first rule, it uses the second one, and it comes up with a number. Because the number 0 is not supposed to use the first piece. It's supposed to go down to where the part of the domain that it belongs to. So f of 0 is 0 squared, which is 0, so yes, it exists. There's step 1. and we check it off. But then we go to try to do step 2. Step 2 says, what is the limit as you approach 0 from the left? So I'm approaching 0 from the left. What number does it seem to be approaching? -4. What is the limit as x approaches 0 from the right? It's 0. Are these the same?
No.
No. Therefore, the limit as x approaches 0 does not exist because it's approaching two different numbers. It fails the second step of the continuity test. So if you go back to the problem, it is discontinuous at x equals 0. There's where the problem is. Those two pieces do not connect. It is continuous, however, at x equals 3. This one worked. So if you're working with a piecewise function, the method is look and see what happens to the value of the function at the places where it changes rules. The first one and the second one change rules at x equals 0. So at that point, does rule 1 and rule 2 give you the same answer? And it didn't. Even though it existed, because rule 1 and rule 2 gave you different answers, you're coming at a limit from two different places. And you're not coming together, you're coming separate from each other. Okay? But when we do the other rule change, it changes rules again at x equals 3. But the value of the second rule at x equals 3 is exactly the same as what we would have gotten if we plugged it into the third rule. So when you do your limit, you're coming together at a single value, which in this case is 9. Okay? We've got one more problem. This one's actually not going to be that hard. A trailer firm charges a flat $8 to rent a hitch.
Bless you.
The trailer itself rents for $22 a day or part of a day. Let C of X represent the cost of renting a hitch in a trailer for X days. Now, before we try to graph C of X,
What page are you on?
I don't think it's on the
I don't think it's on there.
Just in the book?
It's just in the book.
Okay, what page down in the book?
It'll be at the end of section 11 too. So this is just, we just did a piecewise function. You saw that piecewise functions have a great potential for being discontinuous, even though it doesn't break any algebra rules. It's a law-abiding citizen, but it still can be discontinuous, so it can still misbehave a little bit. Let's talk about what happens here. X days. What's the least number of days you can rent that trailer for?
0.
Okay. What does it cost you to rent the trailer for 0 days?
$8. 0.
0, because you're not going to rent the hitch if you don't rent the trailer, okay? What does it cost you to rent the trailer for a half a day? That's not a trick question. What does it cost you to rent the trailer for half a day?
$15.
$22, because you have to pay for the whole day. You don't just get to keep it for half a day and pay half of the rent. But what do you have to get the trailer out of there?
A truck.
What do you have to have besides the trailer? You gonna grab a hold of it and pull it?
Something to pull the trailer. I said a truck.
Insurance.
That's the wrong person.
You gotta rent the hitch. Okay, you have to rent the hitch to rent the trailer. Otherwise, your renting trailer is gonna stay there in that parking lot. Okay? So if you rent the trailer for half a day, it's gonna cost you $22 plus $8. That's $30. What if you rent it for a whole day? For a whole day, it costs you $30. What does it cost you for a day and a half? It costs you another $22. You don't have to rent the hitch again. You rented it. It's rented it. You don't get a per day charge. Okay? But if you're keeping the trailer another day, it's going to cost you $22. So this is going to be $52. And if you keep it all the way up to 2 days, it's going to cost you $52. But as soon as I go into the third day, whether it's an hour, 4 hours, 6 hours, 9 hours, half the day, or all day the third day, what does it cost me now?
74.
Another $22, which is $74. And for 4, as soon as you pass midnight on that third day, you're renting it for the 4th day, and it's going to cost you $96. Okay? So does everybody kind of have the picture of how this works? That's what the graph looks like. And that bears out everything you just told me. If you don't rent the trailer at all, you don't pay anything because you don't need the hitch. But as soon as you rent the trailer, you're going to get charged for a whole day plus the cost of the trailer. So here's your $30 mark. You don't pay $30 if you don't rent the trailer. That's why there's a little hole there. But you're going to pay $30 regardless of how long you keep it for that one day. If you keep it for an hour and bring it back, it costs you $30. You can keep it for 12 hours and bring it back, it costs you $30. But as soon as you go 1 minute into the next day, it costs you $52. And that's the whole second day. Then it jumps again as soon as you go 1 minute past midnight on the third day, and it jumps up to $74. What are all the values for which C of X is discontinuous? At what values is this function discontinuous? Where does the right-hand limit not equal the left-hand limit? Should be an easy answer. Where does the function come in like this? Sharp jump. Limit this direction is 30, limit this direction is 52. Limits don't match. Discontinuous. Limit this direction doesn't match limit this direction. Discontinuous. Limit this direction doesn't match limit for this direction. Discontinuous. And it would continue being discontinuous at every integer value for x, but only the integer values. Okay? Only exactly 4, only exactly 3. That's where the discontinuity occurs. Okay? And it violates the right and left hand limit rule. Okay? Now, since I worked one of your problems for you in class, I want you to do the 11-2 in-class activity for your homework. That means you need to apply the 3-step test to all of those. Okay? So submit that for a grade. I did one of your homework problems for you. I want to make sure you got this. And I need to see that before Thursday.
Bringing on 20 videos on actually studying it.
Okay. So you can find all of them.
I haven't actually yet, just told me.
Okay. Because I did respond to you. I thought when you said Thursday, you changed the due date.
You said till Thursday?
I need to see that class activity 11-2. I need to see that before Thursday.
Okay, so it's not due today.
No, it's not due today. It's like
It says it
tomorrow
on the
night.
thing, so I was double checking.
Yeah, but it'll be tomorrow night. I'll let you know tomorrow.
This one, so you want us to do